Reinforcement learning is one of the unique methods in AI. That this method is revolving around the agent. What we are trying to do in this method is to train an agent to take the best possible action in order to achieve what we are basically trying to do. For example, we want to train an agent to drive a car, then the agent has to take actions to steer the car, to control the accelerator and the brakes and so on to drive the car. Or we're trying, for example, to control a machine that the agent will change specific parameters in order to get the best possible outcome from this machine. So, as we said, the most important in here is the agent. The reinforcement learning is the agent will take the action. The action will change the environment, or what the agent will see as a change in the environment, and for that he will get a different situation, a different state, and he will get a reward. That is the agent. Of course, we call it he, but it's a computer. So the mechanical like the possible applications of the agent is, of course, we can use it for mechanical control or in general engineering control applications. We can actually use the agent even as an optimization method, that the agent will try to set a specific parameters, and as he will experience the environment and for example evaluation function in this case, he will try to change these parameters in order to get a better and better result. Of course, such a thing, of course, we will mainly train a one agent, but that doesn't mean we only can train a one agent. There is also machine learning policies or methods that we actually train multi-agent. So, for example, if you are in a football match and you want to train these players to achieve the winning, so with the agent in this case is not just one agent, it's all the members are different agents and they all trying to achieve the same reward, which is winning the game. So in total, we can understand that an agent will take action, and from that take action in an environment, and as he will change the or affect the environment will return to him another state. So his situation, for example, it's a game, his position got changed, so now he has a different state, and based on that action for that specific state, the state he took the action from, he will get reward. So this is basically the idea. This is kind of a process we can see, which kind of also what we do as a human, or like also as animals, that we have environment and we interact with the environment and we get reward, or we get punishment, which is, you can say it as minus reward, and we will change our state. So of course the mathematics and the ideas behind the reinforcement learning is not very new, but of course with machine learning and the possibility to use a high computational model, high computational power and a lot of data, we can of course build a quite strong agents, and these things are evolving. And of course reinforcement learning in general is it's most likely that the way we will get a general intelligence is going to be a big part of it is reinforcement learning, because we need an agent that will interact with the environment, which is not very easy to do it with other machine learning methods. So of course, if you were interested to learn more, you can also go to this. I would recommend this book, Reinforcement Learning: An Introduction, for Sutton and Parto. they wrote this book, and you can just take this link. It's a free book, so you can just open this PDF link and you just read it. So as we talked about that, we said this thing looks like a process, that we have the agent take an action, the action of course impose on the environment give it back another state, will turn to him another state, and he will get reward. So this kind of idea, the idea of first a process, and the other thing is the idea that there is a unique state, is we have a unique state, and from that state we can take another action, is it is the kind of the basis of the Markov decision process. And Markov decision process, of course, it's considered there are unique states, and it takes another thing, like the most important, also another important thing in Markov decision process is basically that the future state does not depend on the history of our states. For example, if we have a current state, the future state will depend only on our current state. It does not depend on the past state. It does not depend on the past actions. It depends only on the current state and the action that we're going to take in the current state. So this is a very powerful idea. That means we have everything in the environment will be a unique state, and from that state we just simply take an action. So we don't have to care about what happened before. Another thing we can say, like this diagram, we can look into this diagram as kind of representation of like Markov decision process, that if we have an action, if we are in action is 0, and from we are in a state is 0, and we took action A0. If we took the action A0, we will have a possibility to go to state 2 or go back to state 0. Now, this possibility we call is a transition function, which is simply the probability of going to one state or another state based on the action we took. Of course, if we took, let's say, action 1, we have only one, the transition function is 1, which is basically we will go to S2 or state number 2. So basically, this is the idea. A state 0, we take an action, we go to another state, and in between there is a transition function that in our in some machine like on reinforcement learning problems, you might have if you take an action, there is a possibility of different things happening, so you can use this transition function. Of course, if you took some actions will give you, or some actions will give you rewards. Like, for example, if we move from or we took A1 here and we moved to S1, we might take a reward, in this case -1, which is kind of punishment. Or you can go, for example, if we take S1 to S0 and taking action A0, we will have a reward of +5. It's as simple as this. It's just going from one state to another, completely independent state, completely unique state, and every state will have different actions connected to it, and these actions will take you to another state, and we will get rewards as you take this action. Another thing we have to care about, or some kind of state, like words we have to consider, is the state value and action value and policy. This vocabulary thing we have is it looks a bit complicated, but it's not. It's just like a state value is simply when you have a state that you want to measure how good is this state. So if I have S and S slash, so this S and this is a state S and this is state slash, which is better. So we take this state value, we give as every state will have a state value that it is is connected with the expected reward that we might take if we continue the game or continue the the problem we're doing. So if we are continuing the game, we are in state, and when another state is slash, if the possible rewards going to be higher in state S than S slash, then we say that the value of or the state value of S is higher than the S slash. Of course, when we say expected reward is kind of hypothetical. We say expected rewards taking a specific policy or the same policy in both. And again, policy is simply the mapping of the states and actions, or how what kind of methodology or the agent will follow at specific states in order to achieve the highest possible rewards. So this can be Q table, can be a deep Q network or DQN, or other methods. So this is basically what we call as a policy. Now, there is another also item here or vocabulary we use is the action value. And the action value is if we are in a state and we have, let's say, two actions, so A and A slash. If we took A, we might, the expected reward in the, if we are in that particular state or taking that particular action, the expected reward will be a specific number. So this is going to be our action value. And of course, if we have S slash, then again, we have a different action value, because the expected reward that we will take starting from this state, taking this action, which is A slash, for example, will be different. Of course, take into consideration that both of them will follow the same policy, which is again the same way the agent will take actions in particular states that is going to come. So in Q table, which the method we will code from the beginning, and later we will use libraries to actually change these policies or these methods. But for now, what we will do is the Q table. In the Q table, the Q value, which is the action value, the Q value we will calculate it based on the Pellman equation. And this is a very important equation, because we can assist the action. We are in a specific state, and we can assist the actions that we might take based on this Q value. So calculating it is, of course, a very important thing. So how can we calculate it? Well, we follow this simple equation, which is Q new at the new value of Q will depend for specific state, and specific action for that state will depend on the old value of Q plus learning rate, which this is going to be updated. So every time we will return to this state, we update the Q value. So the learning rate, a value of 0.1 is reasonable, and multiplied by reward plus discount factor, which is the value that we're going to multiply it to max Q. So this is the new state. What is the maximum Q value of the next state? So this is just a constant that we will consider. What is the possible Q, the maximum value of the next Q, minus, of course, this is the time plus 1, like the best Q value of the next states, and we minus the old value of Q, which is this one. And this will be the new value of our current state. So as we will code our problem, you will see how these things will update. But in general, what I can tell you is simply we have the Pellman equation, and we will update that Pellman equation, and we keep doing this every episode. Every time episode means one full game. Every episode we keep doing this, and we keep updating every step. So every time we go to this step, we update until until all the values are converged. Then our learning process is done. Now in the Q learning or Q table, or basically in general in reinforcement learning, sometimes we take greedy action and sometimes we take random action. The reason we take greedy action is simply to win, to achieve what we're trying to achieve, to get the best possible reward at that specific time. Now, sometimes we take random action, and random action, why we take random actions is because random actions give us an exploration. So if you know some specific route to achieve a specific target, then well, that's greedy. You will just go to that road, but maybe there is another road that is shorter. So in order to know if there is that route, you need to take random action. So that we will we can call it an exploration. So this is when you hear exploration and exploitation, these two things, it has to be a balance. Sometimes we explore, that means taking random actions, and sometimes we take greedy action, which is we exploit our moment. So this epsilon will start from 1, and as we go through the update these Q values and these every episode we do, we will keep changing this epsilon, which is epsilon greedy value, which is meaning that the possibility of at this episode we will have random action compared with greedy action. So we start from 1, which is always we take random action, and as the epsilon greedy decreases, the likelihood of getting or going or deciding to go to a greedy solution will increase, and the random tendency to take the tendency of taking random solution will decrease as we our model keep training. Every state from a unique state will send us to another unique state. We can understand it like this. In Q learning, what we have is, for example, a state that is the mouse is starting this game, that he is trying to reach the cheese in here without hitting these red points. When the mouse started this game, or when the mouse starts this game, we can see that it has two options. The first one, it can go to the right and die in this red square. The other option is to go to the below square. Once he change from this state to this state, we can see now he has three options, three unique options. So every state we are in is unique, and this state doesn't even linked to the state before it. And every state will have a specific options, and these options will have options to take actions, and these actions will send us to another unique states that also have different actions and unique and this action is going to send us to another unique states. So this idea, we will learn it more as we code our Q table. So in general, how the Q table works, or how the Q table algorithm works? Well, it starts as any other algorithm. We set our parameters at the beginning, or usually what in machine learning we call it hyperparameters. That is the parameters responsible in the learning process. After that, we will have a random start of a state, or a random state start. After that, we will take action based on the epsilon number. As we said, sometimes it will be random, sometimes it will be greedy. As we take action, we will affect the environment, so that environment will give us a new state. So the state will be updated. After the state is updated, we see what is the resultant reward. So the reward will be given, And as we have the state and the reward, what we can do is to calculate the Q value. So we will update the matrix, the Q matrix, for that state Q value. We keep doing this until the game is ended. After that, we will start a new episode, and we will start the game again. Note that the Q matrix will be updated as these episodes goes in the Q table algorithms. So the Q matrix, we will start from a random matrix with just random values, or we can put it even zeros, and we keep updating it as we go through the learning process. That is, every episode will update the Q matrix a bit by bit, and every step we take will keep updating the Q matrix bit by bit until we have so many iterations that every state we have already experienced many actions that this state the resultant of this state will give us, and this will make us take decision based on our Q matrix. So how the Q matrix will look like? Well, it will look like something like this. For example, in the mouse game, you will have X and Y, and you will have all these X's and all these Y values that represent the location in the game itself, and you will have these actions. Of course, now for simplicity we have only 3 actions, but of course these actions can be in the mouse game it will be 4 actions. So either you go right, left, or up and down. So this matrix with these Q values, that we will get always going to update them, we will take decisions based on the Q matrix. And one thing we have to understand that as we update this matrix, we will monitor the maximum value of this Q, the maximum Q value of this matrix, and we need to monitor how it develops. What we will see is, as we keep increasing these episodes, as we go through these training episodes, which is playing the game over and over again, we will have this Q the Q value, the maximum Q value, we will have it converged. For that, we can consider that the learning process is already finished, and with that we stop the learning process. So this is for Q table. That is, we always have take actions based on the Q value, and always based on this Q value, we will base on our decision on these Q values. So changing going from Q table to just removing the table itself and exchanging it with a neural network, what we find is we can also estimate the Q value, and we can train the model as we keep updating the matrix. We just keep updating the model, so we can replace the Q table with the deep Q network. So this we will do this. We will actually code our Q table, and we will exchange that with an actual deep neural network, which we can call it deep Q network. The example or the problem that we are going to solve is a simple problem, a simple control problem. That is, we have a room and we are trying to control the air temperature in this room. The temperature should be between 26 and 24, and if the agent succeeded to keep the temperature between 24 and 26, he will get a reward of +1. If the agent made the temperature higher than that, he will get a reward of -1. And if it's become too cold, that is lower than 24, again he will get again a penalty or a reward of -1.